actually launching 168 sounding rockets in that amount of time was a resounding success in retrospect. Of the 19 satellites launched, only 7 satellites were launched, and in fact, they were only the small ones. The 2 large astronomical satellites, LAS-1 and LAS-2, actually spun out of control in terms of budget, and there was some political disagreements, perhaps, on how the satellite should be built, where it should be built, so on and so forth. So, so those were the missions that ESRO had managed to fly, and you can see not all of them were successful. ESRO 2A, if you can see my mouse, ESRO 2A launched, but failed immediately. ESRO didn't last as long as it should, so on and so forth. But we had some quite successful missions as well, with the highly eccentric orbital satellites 1 and 2. On the ELDO front, the Launcher Development Organization, things weren't quite as successful. All the rocket launches that they had called Europa had failed, and they were launched from Australia. And you can see here successive failures. And then eventually Europa 2, which was a slightly more powerful rocket, which was launched from French Guiana, also failed. Well, I mean, the first 2 stages were perfectly fine, but the third stage, I understand, failed. So that was also considered as a failure, or partial success, if you're looking at it from the positive side. So it was clear that things weren't going according to plan. Certainly on the ELDO front, the French were very keen on maintaining a launch capability within Europe, and they started branching off into their own program known as Ariane, which subsequently would be used by ESA, of course, as a launch facility and launch service as well. So from 1971 to 1975, people wanted to reform a little bit how ESRO and ELDO were functioning, and it was toyed with the idea that actually ESRO and ELDO should be merged together and act as one agency. And so that led to the 1975, when a new convention was written, known as the ESA Convention, and this was signed by 10 member states. And I should say also that actually before ESA Convention was signed in the early 70s, NASA and ESRO had agreed to various missions called Space Lab, which would be some scientific labs flown inside the shuttle. When those missions came to fly, of course, it was under the ESA flag. So, yes, 1975, the convention, the new ESA convention is signed by 10 member states. You can see them highlighted there in the map. And the purpose of ESA was clear, that it should be to promote, for exclusively peaceful purposes, cooperation among European states in space research and technology and space applications. So I'm going to skip forward to quite a few years now and show you how ESA is governed. So the convention states that 2 bodies are responsible for governing ESA. It's the ministerial, or the council, but I'll refer to it here as the Ministerial Council, and the Director General. On one side, the council is supported by various bodies and committees that advise the ministers who are appointed, very much like it was in ESRO. So each country is represented by 1 delegate. And so just to pick out a few here, we have these committees and these boards who meet between 2 and 4 times a year. And for example, here, International Relations Committee, if I pick that one up, so it has 2 main tasks: assist the Council in coordinating the policies of all the member states in the space field, as well as other national and international organizations. so that we have a common view and a common position amongst international bodies. Another one, for example, the SPC, the Science Program Committee. It's the committee that advises the Council for all matters that form part of the mandatory scientific program. You'll understand what mandatory and optional programs are a little bit later in a couple of slides, but there are other activities within ESA which are not mandatory. So this is launches, for example, Earth observation, human spaceflight exploration as well is not mandatory. But all of these boards advise their ministers on the activities of ESA. As I said, yeah, these little sub boards and committees meet 2 to 4 times a year, advise the ministers, and there's a big ministerial council which happens usually every 2 to 3 years. And this is where the big decisions are made and reported back to the Director General. So on the other side of the coin, I said we had the Director General. Of course, it's not just one person. The Director General, for anybody who doesn't know, is Joseph Aschbacher from Austria. He's supported by a panel of directors, each with their responsible directorates. So you can see here the Director of Science, Human and Robotic Exploration Programs, Space Transportation, so for launches, European legal internal matters. So this is more not so much about the scientific activities, but more the running of the agency as well as the internal services. But we have operations and we have tech, engineering, and quality directorates as well, telecommunications, and so on and so forth. And just to give you an idea behind each of these boxes, we're not going to look at this in any detail, but behind each of these boxes, we have, so this will be directorate level, then we'll have different departments, and within these departments, we'll have divisions, and then within these divisions, we have units. So you can see it gets very complicated very quickly. And in fact, on this side of the coin, this represents about 5,000 people who work at ESA and for ESA. Okay, so it's quite a complicated structure for the agency, but it works well. And in fact, it works so well that since 1975, we've increased the number of member states, sorry, from 10 to 22. So we also have some cooperation agreements. So it's not full member states, but for example, Canada, Bulgaria, Lithuania. Slovenia, Latvia, and Lithuania are associate members, and we have some cooperation agreements with Canada, Malta, Slovakia, and so on and so forth. So that's the number of member states we have today. I mentioned that ESRO had developed some of these sites that were part of the executive branch, and those sites still exist today. We've got a few more in addition to what we had back in the 60s and the 70s. For example, here headquarters are located in Paris. ESRIN is now the Center for Earth Observation Activities, and that's near Rome in Frascati. But it also hosts the Vega program, which I'll talk about a little bit later. ESTEC is actually where I work. It's in the Netherlands, and it's the site where missions are devised and satellites are tested, basically. ESOC still exists, and that's the European Space Operations Center in Darmstadt in Germany. And also in Germany, near Cologne, in the DLR facility, we have the European Astronaut Center, which hosts astronauts and trains the astronauts as well, not only from Europe, but from the United States of America, and also from the cosmonauts from the Russian Space Agency on European elements of the International Space Station. We have some sites in Spain, Villafranca, ESAC, the Space Astronomy Center, basically hosts the science operations and archives all the data from the astronomy and planetary missions. We have some sites in EXAT, the newest one, I believe, focus more on commercialization and partnership and space activities. Redu also actually hosts a large portion of the education program, but we'll talk about that a little bit later. But it also has a ground tracking facility and is involved in cybersecurity these days as well. And importantly, on the other side of the world, in French Guiana, we have the Guyane Space Center, which hosts basically the CNES, the French Space Agency, and the Ariane Espace program, and it's basically our gateway to space. Okay, so let's have a quick look at the budget for 2022. Well, if we focus down on the figure down below on the left, 7.15 billion euros for this year. That's a tremendous amount of money, of course, in anybody's bank account. But if you compare it to NASA's annual budget for 2022, which is 24.5 billion, or the equivalent of 24.5 billion euros. So we're operating all our activities with less than a third of what NASA is operating theirs, just to put things into context. So this pie chart here, what does it tell us? It tells us how much each member state is contributing towards ESA activities. So you can see that the main contributors are France with 24.5%, Germany with 21%, and Italy with 14%, and so on and so forth. So you can look at your own member state there and see how much is contributed to the ESA. It's important because of this juste retour that I mentioned to you before, this GEO return. So obviously, if France are committing 24% of the ESA budget, they expect that the majority of this money will be awarded back to French industry for developing hardware and facilities that will support whatever missions they have planned. And we can talk about the domains in the next slide. So yes, that's the concept of juste retour and GEO return. Down here, another considerable portion of the ESA budget comes from the European Union. I hope that you will have understood by now from the history of ESRO and ELDO that ESA is not part of the EU, but we do have major programs of Earth observation and global navigation satellites programs with the EU, and they fund us quite a large proportion as well there. Other programs such as EUMETSAT, which are meteorological satellites, so organizations that have split from ESA and basically operate these satellites. So that's the amount of money that we get from the ESA member states, but what's also important to look at when we're talking about the money is where this money is distributed, or how the pie is cut after the money has been awarded. So we have some activities here which I've put inside a box, and this box is basically, or these boxes represent the mandatory program. And I'll explain that in the next slide. But you can see here also that from the non-mandatory programs, so the optional programs, things like Earth observation, space transportation, and navigation tend to get a large slice of budget in order to operate these programs. So I mentioned mandatory and optional programs. So what is a mandatory program? Mandatory program is basically the science program, the technology research program, and the basic infrastructure and general services that supports ESA in actually running the rest of the program. So when a member state joins ESA, when it signs a convention, the member state agrees to contribute a fixed percentage of its gross domestic product, and that in all forms about 20% of the ESA budget. At the council, of course, each member state can decide on what else it wants to participate in. Maybe launches isn't something that country is particularly interested in or involved in, or doesn't have any capabilities of doing so. So it won't necessarily fund any funds towards the launcher directorate, for example. The same goes for Earth observation, telecommunications, and integrated applications, and the human space flight and international space station programs. So the council meetings at ministerial level appropriate the distribution of budget to the optional programs, and for the mandatory programs, ESA tends to arbitrate how that money is distributed within the agency. So I hope I've given you an outline of how ESA works, where we get our money, and how we distribute the money and how we spend the money. And now I think is a good time to tell you about what we actually do, so our actual activities. So we have four main pillars: science and exploration, safety and security, applications, and enabling and support. And I'll give you a few examples of each of those, and then we'll finish off the presentation about ESA. Of course, if you have any questions, please write them in the chat, and I'll try and address them at the end of the presentation. So science and exploration, exploring the solar system. So here we go. So this is basically the missions that ESA has been involved in for exploring our solar system. So at the bottom of this image here, you see the various missions that have come and gone. I draw your attention to Rosetta, for example, which was flying for around 10 years or so, doing very complicated maneuvers and flybys, etc., before landing on 67P Comet. So that was a highlight, certainly for me, since I've joined ESA. There's also some other missions like Cassini-Huygens. Huygens was a little probe that landed on the moon of Saturn, Titan. It happened in 2005. So we have quite a lot of legacy. At the moment, these are the missions that are currently active, being operated by ESA. So the Solar Orbiter, launched in 2020. We have Bepi Colombo also, which was launched in 2018. Cluster, looking at the magnetosphere of the Earth. We also had Mars Express orbiting Mars for quite a number of years now, and more recently we've had the ExoMars trace gas orbiter orbiting Mars as well. So quite a lot of solar system mission explorations. And in development, we have a handful as well: Envision, Smile, and you can see ExoMars rover was supposed to be launched this year, but of course, because of the issues, the current political situation, that's been delayed now. But nevertheless, you can see that we have quite a number of solar system explorers in the running. We also observe the cosmos, deep space, and we have a lot of satellites and a lot of legacy in looking at the electromagnetic spectrum. And you can see here this nice little graph that depicts all the satellites that we've operated. Also looking at gravitational waves with the LISA Pathfinder, basically a technology demonstration for a future mission called LISA, which will detect those gravitational waves. But currently active, we have the Webb, of course, that was launched last year in cooperation with NASA and a couple of other agencies. Hubble is still operational. We've got Gaia and Cheops looking at exoplanets and monitoring some billion stars, and so on and so forth. And in the development range, we have also quite a few observing satellites, or cosmos observing satellites, I should say. So very active in the science program. So this is part of the science program. Okay, so I mentioned Rosetta. I hope that, there we go. Also want to draw your attention to the ExoMars trace gas orbiter orbiting Mars. It's detected huge amounts of water on the surface of Mars. This is some of the data that we're getting back from ExoMars. For example, this region here in purple represents 40% water for weight volume, and this is about the size of the Netherlands, so it's a considerable amount of water in this valley on the surface of Mars. I mentioned the rover that was supposed to be launched indeed this year, but will probably be launched much later now. Also to tell you that we're involved in the Mars sample return. So currently we have Perseverance drilling rocks and leaving them in these little sample holders, titanium sample holders, and being dropped on the surface of Mars. And these will be picked up by a mission called the Mars Sample Return, which is being developed by ESA in collaboration with NASA. In terms of deep space exploration, well, the first picture here is a picture of our Milky Way taken by a Gaia satellite. So it's tracking, I think, 1.7 billion stars in 3 dimensions. So it's quite a large amount of data, as you can imagine. And the other picture here is a picture from Planck, which was basically observing the first lights of the Big Bang. So this is microwave cosmic background images, which is, really interesting data for scientists who are interested in looking at the origins of our universe. This pillar also encompasses human spaceflight and exploration. So you're probably all aware that there's currently an astronaut selection program that's undergoing now, and before the end of the year, we should have a handful of new astronauts who will be basically leading the way, not only continuing LEO missions, so low Earth orbit missions in the ISS, but also taking a further step towards Mars. And you know that, well, unfortunately, we haven't had any launch from Artemis lately, and it's been pushed back. But just to let you know that ESA is playing a massive role in this exploration of Moon, of putting man back on the Moon surface, because this module here that you see is a service module for the Orion capsule, which will orbit the Moon. And this is basically legacy from the automated transfer vehicle that was developed for the ISS as well. So we're very active in human space flights exploration aspect as well. Quickly moving on to safety and security branch. So just trying to keep things current. You will have heard of the DART mission that NASA basically plunged their satellite at high velocity into the moon of a binary system called Didymos and Dimorphos. Dimorphos is the moon that's orbiting Didymos, and basically the attempt here was to see if we can redirect potential threat to the Earth should an asteroid or a comet come plunging towards us. Do we have the capability of redirecting it away from the Earth? And so this mission happened just a few weeks ago. It was being observed by an Italian CubeSat as well. We saw some really beautiful pictures of the crash, but also we saw an external point of view of the crash from this Italian CubeSat, Lycia Cube, I think it was called. Really quite phenomenal stuff. And in 2024, ESA will be launching the HERA mission, and the HERA mission will meet the same binary system and will actively and very accurately look at the orbit of the moon to see if we have indeed been capable of deflecting the orbit. And that basically gives us good confidence that we have the capability of saving the Earth should asteroid or comet come hurtling towards us. Space safety is also looking at LEO or various orbits around the Earth. This is a graph that represents the amount of debris that's currently orbiting the Earth. You can see now that we've got about 30,000 pieces of debris that are 10 centimeters or bigger. Of course, this poses a massive threat to the operations of the satellites. We have approximately 2,000 functional satellites at the moment going around the Earth, and being impacted by any part of debris here would be tragic and potentially fatal for the ISS, or fatal certainly for the mission should a collision occur. And so this is basically a graph showing you the debris that's trackable, so 10 centimeters or larger, but it's estimated for ESA models that we have, I believe, over 1 million pieces that are between 10 centimeters and 1 centimeter in size that are not so easily trackable. So the danger is real, and we have to keep an eye on it and make evasive maneuvers whenever we can to avoid collisions, which would eventually lead to even more debris and so on and so forth. So ESA is very active in debris mitigation as well. When we talk about safety, we're talking about space weather as well. So we have a number of missions looking at coronal mass ejections and looking at the sun's activities, looking at solar wind, etc. All these are all potential events that could disrupt satellite operations orbiting the Earth, but also activities on the Earth, so flights, GPS, so on and so forth, or GNSS, I should say. So monitoring the space weather and looking at the sun's activity is also very much in our security branch, or pillar, I should say. In terms of applications, well, I did mention that we have collaborations or programs in association with the European Union, and this is Copernicus is one of those. Copernicus is a series of, I think, 7 satellites now orbiting the Earth and basically observing the Earth. And this is a picture, an example of the type of data that we get from a satellite called Sentinel-5P, and it was monitoring the nitrogen dioxide levels in Europe. And this was before, the first images before the pandemic, and then, you know, the pandemic, the lockdowns, etc. in the year 2000. Not so much industrial activity, everybody teleworking rather than moving to work, or traveling to work, and so on and so forth. And you can see that the massive reduction in air pollution over Europe, and then this quickly reverted back in as soon as the restrictions were lifted and people went back to work and industry could work again. So it's interesting data that we can monitor and also assess the air quality for people with asthma and so on and so forth. So actually this reduction here is approximately 30% reduction in air pollution that we observed during the COVID lockdown. Another example, quite recent, so I know that in August you will have heard that Pakistan underwent some huge amount of flooding, and the Copernicus Sentinel-1 satellite was helping identify the extent of the floods and also helped coordinate the responses in these areas. So again, this is another example of how space can help, Earth observation can help rescue efforts on the ground as well. And even more recently, Hurricane Ian that hit Florida and in fact delayed the Artemis flights in Florida. So here you can see Sentinel-3 picture of Hurricane Ian going across Florida. So yeah, so we're very active in the Copernicus program with Earth observation satellites. Applications is also connectivity. So the EDRS network is basically the European data relay system, or novel system of communicating between satellites using laser technology. It basically allows us to have real-time access to Earth observation data from any satellite around the world. It increases the data rates and also enables us to encrypt the data that's being communicated from Earth to the satellites and back and forth. So we're involved in enabling these sorts of new technologies, and also, of course, Galileo, which is a constellation of navigation satellites orbiting the Earth and allowing high precision positioning on the surface of the Earth. So all technologies that are being developed these days have Galileo chip capability. All the chips are capable of inferring Galileo's constellation signals. The last branch is enabling and support, and here this is a little bit about how we managed to get these missions going. So I mentioned already on a couple of occasions ESTEC, the technology center of ESA based in the Netherlands, where we have state-of-the-art laboratories and facilities that can basically test the latest technologies, but also test the satellites and subsystems of satellites and ready them for launch. This is one of the examples of the test facilities that we have. This is a large space simulator. You can see a satellite here being lowered into a huge chamber, which will be within which a vacuum will be created. Liquid nitrogen is pumped through the black sheath around this chamber to cool it down to temperatures that are similar to space. And on one side, which you can't see from this image, there's a large sun simulator as well, which blasts high amounts of visible light radiation on the satellite surfaces, and the satellite is rotated within this facility, basically simulating the space environment just to check whether the satellite is capable of withstanding these environments. So ESTEC has really all sorts of facilities with shakers and acoustic chambers as well. Large European acoustic facility, the LEAF. It's quite impressive as well, where the satellites are basically enclosed in a chamber, and various frequencies, sound frequencies, are blasted to the satellite, which is supposed to replicate, of course, the noise that the satellite will undergo and be exposed to during launch. And so this is basically to ensure that the satellite survives the mission. We also have the facilities again. I'm referring back to ESOC in Darmstadt, where you can see people busily operating the satellites. And just I want to draw your attention to the board here at the back, which is basically all the missions that ESOC has been involved in operating. So it's a tremendous amount of missions and satellites, and they're doing a very good job of operating these satellites. We also have networks of space antennas dotted across the world. As satellites orbit the Earth, we need to be able to communicate with them. We need to be able to send them new commands. And this is a picture of one of ESA's antennas in Australia. But we have some in Spain, Argentina, and so on and so forth. And it's not just monitoring ESA missions. There's, of course, a lot of collaboration with NASA and other space agencies, where this network is also used for tracking their missions. I mentioned earlier also the spaceport in French Guiana. Still in operation today, of course, and we launched quite a number of missions from there. I think over 200 flights. I don't have the exact number in my presentation, but it's really quite an incredible amount of launches. And on the right, you have Ariane, the CNES rocket, or the Ariane Space rocket, I should say. But on the left, you have the latest launcher developed by ESA, which is known as the Vega, the solid propellant rocket. And so, yes, so our access to space is enabled basically by having this spaceport in French Guiana, which is close to the equator. So that's, I want to conclude the presentation there, just in time for the hour. Of course, it's a fleeting view of what ESA is, but I hope I've given you a little bit of everything, from the governance, to the history, to the governance, to the actual activities. But if you want more information, please email us at petri.academy@esa. If not, I advise you, if you don't want to write to us for any reason, you can also visit this great website, which is discover.esa.int. There's a lot of information about our activities. There's also some pretty cool 360 tours that you can take of all our sites, and there's some videos that explain some of our activities, so on and so forth. So that concludes my talk.
Okay. So after the presentation, you have just heard from Nigel about ESA in general. I will now go into depth on ESA Education, ESA Academy, and its Petri program. I would also like to introduce myself. My name is Felix Scharnholz, and I studied aerospace engineering at the Technical University in Dresden, Germany. And during my studies, I participated in some hands-on projects, a European Rover Challenge, an Erexus mission, and did some internships on the locomotion ground testing of the ExoMars rover in Switzerland and on in situ resource utilization of oxygen from moon regolith at the EAC in Germany. And afterwards, then I started as a young graduate trainee in the coordination of the Rexus Bexus program, so in ESA Academy in 2021. And currently, I work together with Nigel on the realization of the Petri program. I will start my presentation with a bit in general about ESA Education, and then I will talk about ESA Academy and its programs. So why is education so important to ESA? As you have heard from the previous talk, there is a convention for the establishment of the European Space Agency, which has been signed upon the founding of ESA. And in this convention, education is a mandatory activity and the reason ESA Education exists. So what are our objectives? First, to motivate and enable young people to enhance their literacy and competence in sciences and technology. To inspire and enable young people to consider pursuing a career in the STEM field and in the space domain in particular. And last, to contribute to increase young people's awareness of the importance of space research, exploration, and applications in modern society and economy. ESA Education targets pupils and students from primary education to university level or after university level even. So this comes with multiple challenges since we have 22 member states, and if you count the cooperating states and Malta, where we have a special contract with, we target actually 26 member states, 26 states. And in these 26 states, we have 80 million school-age pupils, 7 million teachers, and all of this in 17 languages. And yeah, additionally to that, there's also a shortage of specialized workforce in the space sector. So as you can imagine, it's not easy to reach all these people. And to still achieve our objectives, we have a diversified approach. We target pupils and teachers with formal and informal education, so teacher training and resources to support them in giving a curriculum, but also hands-on projects within the classroom. So for that, we have the Cancer Project, MoonCamp, AstroPi, just to give some examples. And university students, we target mostly with hands-on projects. Here we have satellite projects, but you can also have scientific experiments or technology demonstrators which you fly on our platforms. And additionally to that, we give academic support in form of courses and workshops directly to the students or by sponsoring participation in conferences. And the first approach is bundled in the ESA STEM program, while we target university students with the ESA Academy program. So in the rest of the presentation will be focused on ESA Academy as you are the targeted audience for this. The ESA Academy program is divided into three pillars. Space to Mind and Matter to Engage targets mostly individual university students, while the pillar Mind to Matter targets student teams. Space to Mind comprises our training and learning program, which consists of courses and workshops we give, as well as longer duration training programs like summer schools. And Mind to Matter, we comprise all our hands-on programs. So the Rexus program, Flyer Rocket, Flyer Satellite, and now also the Petri program. On these programs, I will hold most of my presentation, so you'll hear more about that. And then Matter to Engage consists of the sponsoring of space conferences and internships, which you can. So Space to Mind. Space to Mind, as you just heard, consists mostly of our training and learning program. So what are the objectives of this program? We want to complement the standard academic knowledge which you receive in university with space-related disciplines. We want to attract future scientists and engineers to the space sector. And of course, we want to prepare this future workforce better for the work in the space field. This is done by transferring knowledge, know-how, and industry standards via training sessions and summer schools. And for this, we have a dedicated facility in Redu in Belgium on the ESA site ESEC Galaxia, which is called the Training and Learning Facility. A course of the training and learning program consists minimum of 32 training hours and targets 30 to 60 university students. During a course, there are usually 1 to 6 trainers per day, and they come from ESA, but also from space industry and academia experts. This training, such a training program does not only consist of workshops that are given by these trainers, but also of group projects and exercises the students have to do. And in the end of student presentations and then evaluations by the trainers. And by providing a transcript and a certificate, the students participating can claim ECTS credits at the university for the programs they participated in. On this side, you can see the portfolio of the training and learning program. So as you can see, it consists of a variety of different training sessions, but also of 2 summer schools, which you can see on the bottom in green. On the one, the ESA Algor Summer School, and then the CubeSat Summer School. They're in principle similar to this training sessions, but instead of being in the course of a few days, they're multiple weeks long. So Mind to Matter, our hands-on programs. The Mind to Matter pillar comprises 4 programs: Flyer Rocket, Rexus, Flyer Satellite, and Petri. And Petri replaces the previous Your Thesis program. So Fly Your Thesis, Drop Your Thesis, Orbit, and Spin Your Thesis. Okay, a bit on depth on each program. In the Flyer Rocket program, you can apply every 2 years. It's targeted to bachelor level students. And the program consists of an online course and a rocket launch campaign. The course is on various topics regarding rocketry, atmospherics and aurora physics, but also soldering and telemetry. And then during the launch campaigns, the students can build, test, and then finally launch their own sounding rocket by working in different teams during the campaign. And there's a call for Fly Rocket is still open currently until the day after tomorrow at midnight, so the 9th of October. And then again opens in fall 2023. Yes, Rexus. Rexus is a program where you can launch an experiment on a sounding rocket to about 80 kilometers high which also gives you 2 minutes of low gravity to conduct research. You can apply to the Rexus-Bexus program every year, but between the selection and the launch of the respective Bexus balloon, you have about 1 year to develop your experiment, while you have 1.5 years to develop of development time for Rexus, for an experiment on Rexus. And the calls are currently closed, but will open again in summer 2023. During the program, you will receive trainings, lectures from our side and industry experts, and then you will develop your proposed experiment to be flown on either Rexus or Bexus. And we will review your experiment or your experiment design together with industry experts, and then in the end, if everything goes well, you can go to the launch campaign of the vehicle you develop your experiment for. Bexus is very similar to Rexus. In principle, you do the same, but you develop your experiment not for a sounding rocket, but to fly on a stratospheric balloon. As a balloon flies on about, or the float phase is about a 20 to 30 kilometer altitude, and depending on the requirements you have in your experiment, you can float for more or less 2.5 hours. And the development and the reviews and the lectures you receive are in principle the same as with Rexus, but of course targeted towards your Bexus launch platform. And finally, then there is a Fly Your Satellite program where university students are selected every 2 to 3 years to get support for their CubeSat mission. Fly Your Satellite offers a program for teams to finalize, test, launch and operate their 1 to 3 unit CubeSat with expert support along the way. And thus this program is aimed at more advanced teams. If your CubeSat is not that far yet, then the Design Booster program might be the best program for you. Here your team and CubeSat gets support in developing the CubeSat design to a more consolidated design. And after the Design Booster, your CubeSat should then be in a good state to apply for the regular Fly Your Satellite program. If you have already a technologically mature model, so it's mostly assembled, procured, integrated, and only needs to get the test campaign done, or needs support in terms of facility, then the Fly Your Satellite Test Opportunity Program will be the right program for you. And for the Design Booster, the call just closed. And for the Test Opportunity Program, there might be a call opening soon. The Fly Your Satellite and the Test Opportunity Program, as well as the Design Booster Program, all make use of the CubeSat support facility. And this facility is together with the training and learning facility in Radu in Belgium and the ESA Galaxia site. And yes, there we have a bunch of equipment for vibration testing, TVAC testing, but also vacuum oven, equipment for electromagnetic interference testing, and workshop to manufacture parts of your CubeSat. So finally, the Petri program. The Petri program is open to bachelor, master, and PhD students. This is platform dependent. Depending on which platform you apply for, your experiment might be more or less complicated. And then we, of course, expect different experience levels from the teams. And the teams must be from eligible countries. You have just heard from Nigel about those member state countries. The program is supposed to give student teams an introduction into the professional world of research and development of space science and technology with the European Space Agency and its partners, that then complements the university students' academic journey. The program enhances on the consolidated your thesis programs by offering this obligation-free training, for example, the webinars right now, but also coaching and consultation prior to you submitting an experiment proposal. And then hopefully armed with the necessary knowledge from these webinars and the consultation phase, you within a team can submit a strong proposal for an experiment idea on a platform of your choice. And yes, if you're then selected, you're guided through all the steps of developing your project from concept to operation and data analysis, including industry standard engineering practices, but also project management, risk mitigation, fundraising techniques, all these things that are important around the technical side of developing an experiment. And we offer to fly your experiment on multiple platforms, which are the large diameter centrifuge, the drop towers at SAM, the Air Zero G in a parabolic flight, and to fly on the ice cube facility on the ISS. And we look into possibly adding further platforms in the future. But in the remaining of the presentation, I will focus on the 4 platforms we offer. The program is structured into 4 phases with different scopes. You can see the affiliated deadlines for each phase on the left. So the first phase offers obligation-free access to trainings and informations, upfront application in form of webinars. And these webinars in the first phase focus on broad topics to give you an introduction into the scope of the program and possibilities and restrictions of the platforms we offer. And then in the webinars in the second phase are a bit more, they go into more technical details on systems engineering and on project management. And during the second phase, while you still receive webinars, you should start filling in your experiment proposal. And if you have any questions, you can just write us an email, and even if it's on your application itself, we will try to help you to make the best proposal possible. Phase 3 is submit and succeed, and it starts with you submitting your official experiment proposal. And this proposal will be reviewed by a panel of industry professionals and ESA experts. And depending on the number of applications, we might shortlist them first, and then the shortlisted experiments are invited to present their project to a selection panel in form of a presentation, and then also you will receive questions on your experiment proposal, which you have to answer to this panel. And yes, if you're then selected, you can start making your experiment idea reality with our support. We will continue to give you guidance and counseling by us and by our partners. And within, depending on the platform, 9 to 15 months after the selection, you can hopefully develop hardware from your idea and fly your experiment. So the platforms we offer. Currently, we offer the Ice Cube facility. It's an experiment rack on the ISS, 2 drop towers in Bram on the SAM facilities, the Air Zero G, that is a parabolic flight airplane, and the large diameter centrifuge, which is at ESTEC in the Netherlands. And I will give you a short overview on this platform next, but the next webinar also gives an in-depth lecture on each of these 4 platforms. And very importantly, before you apply to us, you have to read the documentation on each platform to see what the platform can offer you, but also what are the constraints of the platform. So you don't write an extensive experiment proposal to us, and in the end, you apply for a platform, but your experiment is not feasible on this platform. So first, the large diameter centrifuge. It's located at ESTEC on ESA grounds in the Netherlands, and it can simulate gravity or hypergravity between 1 and 20 G. So this is the one platform that doesn't offer you microgravity, but that actually offers you hypergravity. And combined with that, there is also a random positioning machine where you can simulate microgravity for your samples. And you can run, depending on which length of test you want, you can subject your samples to hypergravity between short duration tests, but also a maximum of 2.5 days consecutive hypergravity or simulated microgravity. The drop towers in Bremen consist of the large drop tower, where you can either drop your experiment in vacuum or you can catapult it up to then be dropped in vacuum, which gives you a maximum of 9.3 seconds of microgravity in a very high quality microgravity environment. And then there's also Gravitower Pro. If you decide to have your experiment on the Gravitower Pro, that means that you switch one drop and the drop tower for multiple 100 drops in the Gravitower Pro. This is a smaller tower where you don't have vacuum conditions inside, but the capsule drives up and down on a train. So you can select the gravity range you want for your experiment and test if your experiment actually works in the drop tower in a specific gravity range you select. The Air 0G is a parabolic plane we offer you as a flight platform. It's the Airbus 310, and it flies from the Novus Bus facilities in Bordeaux in France. This platform offers you longer duration microgravity in a bit lower quality. And longer duration microgravity means that you have microgravity for 22 consecutive seconds, and this for each parabola. And you can fly on 31 parabolas on 3 flights each. So overall, close to 100 parabolas with each 22 seconds of microgravity. Yes, and then the last platform, the Ice Cubes facility on board the ISS. This is the right platform for you if you either need high quality microgravity for a long duration, so up to 4 months, or if your experiment needs to orbit the Earth for maybe another reason. For example, to measure something in the magnetic field of the Earth. And yes, flying experiment on the ISS usually requires a bit more complex operations. So these teams should form around a PhD or multiple PhD students, which can then be supported by bachelor and master students. Yes, if any of those platforms seems the right for your experiment idea, you should definitely apply to the PETRI program. Applying to the PETRI program means that you have to write an experiment proposal. You can find the template for your experiment proposal on the website of the PETRI program. And before you submit the experiment proposal to us, you should use the consultation phase to ask us for feedback on your experiment proposal or to ask any questions you might have. And together with this experiment proposal, you have to submit a video which should be in the style of the elevator pitch. The reason for this is that outreach will be a very important part during the realization of your experiment, because you need to get funding for experiments somehow. Maybe you need components or support from companies which you can't afford otherwise. And for that, it is important that you make outreach to your stakeholders. And so that we can see how you're doing in that, we ask you to make a social media account on one of the named platforms here, and then upload this elevator pitch style video on each of these platforms, or at least one of these platforms. And together with the elevator pitch style video and the experiment proposal, you need to submit a letter of endorsement from one or multiple endorsing professors or your academic supervisor, and the consent form, privacy consent form, which is signed by each team member listed in the experiment proposal. The template for the consent form you can also find on our website. Yes, and then to our last pillar, matter to engage. It's quite short to explain. That consists of us sponsoring students which want to go to a conference which is usually space related. So we would we would sponsor the registration costs, travel, and also the accommodation cost for the students for certain symposia, which you can find on the ESA Education website. And yes, this usually are the ALGRA symposiums, the International Aeronautical Conference, or especially the SSEAC, which is a symposium on space educational activities, and it's organized by the ESA Education Office. Yes, so as you can see on the development of the your thesis programs to the Petri program, ESA Education is evolving to keep up with the evolution of the space sector. And yes, this means that we try to enhance our program so they consist of new trainings, models, and challenges to incorporate hackathons and downstream application projects. But we also want to try to target a more enlarged and a diversified audience. We do this by opening up to people that were not targeted with our programs prior. So technicians, for example, which could receive vocational training, but also young graduates and early career professionals from non-STEP backgrounds. So business, law, as you can see here, also agriculture, architecture. These are all backgrounds which can also have a career affiliated with space, and so can receive training from us. Besides enhanced program and a large audience, we also try to give trainings and lectures on new knowledges. They include cybersecurity, artificial intelligence, but also more software-related courses or courses on climate, environment, space safety, security. All the examples you can see here. We do realize that in a modern world, maybe not everybody has the same schedule and can, come to our facilities to take part in the training. So we incorporate e-learning, personalized learning, where you can go to a platform and receive the learning at the time that fits your schedule the best. And yes. With all of this, we hope for increased impact of our programs and to have opportunities for a higher number of participants. Besides all the training programs you have just heard about, there are more possibilities to work with ESA. To be specific, there are 4 different programs which are open to students and recent graduates who are a national of one of the ESA member states or cooperating states. For one, these are internships, which are available if you're in your final year of your bachelor's degree or if you are studying for a master's degree. Then it's a young graduate trainee program, which is for students who are about to graduate from a master's level course, or for those who have recently graduated, as well as a national trainee program, which is similar but only available to the citizens of certain states, which are Belgium, Estonia, Ireland, Luxembourg, Portugal, and Switzerland. If you're a postdoc, you can apply to the Research Fellowship Program to carry out advanced research related to space science, space applications, or space technology. And PhD or postdocs can apply for ESA to have their space-related research co-funded by ESA, or if they need access to the STEC laboratories or technical support by ESA experts. And more information of each of these opportunities, what is required for these positions and what you can expect from these positions is detailed under the link on the right side of the slide. Yes, and with this, I come to an end, and I hope that you can give feedback to the entire webinar. For this, we have a feedback form. You can see the link on the slide.